Alright, so if we have a molecule and under certain conditions the molecule acts like an acid and under certain conditions it acts like a base, this is what we would call an amphiprotic or amphoteric. So we have amphiprotic, that's one way of saying it, but then also amphoteric. I'm not entirely sure why there are two different words that sound very similar that mean the same thing, but I have seen both of those, and I've even looked up the definitions, and both of them mean the same thing. I don't know. I don't know why we have two words to say the same thing that are so similar. Anyway, we would call these molecules amphiprotic or amphoteric, molecules that could behave either way, just depending on what happens. So for example, here we have bicarbonate ion. And the bicarbonate ion, if it acts as an acid, remember our definition of an acid is that an acid is a proton donor. So if it acts as an acid, it's going to lose H+, which means it would have that. It would become this. It would become carbonate if it acted as an acid. But on the other hand, it could very easily act like a base, in which case it would be a proton acceptor and become carbonic acid. So bicarbonate ion can go either way. It just depends on whether you pair it up with something that's a stronger acid than it is, or if it's reacting with something that's a stronger base than it is. It can go either direction. Same thing here with the is that called bisulfate? I think it is called bisulfate. But anyway, HSO4 minus, if it acts like an acid, then it loses an H+. And so it becomes SO4 2 minus. And if it acts like a base, which it practically never does, but it is technically possible that it could do that, it would go back to being H2SO4. And then lastly here, water, if it acts like an acid, it's going to donate H+, so it would become OH minus. And if it acts like a base, it would accept an H+ and become hydronium. Now the most common mistake that students make when they're working out what something will become if it acts like an acid or a base is you forget the plus. So you will add in an extra H, or you will subtract an H, and you'll forget that you're also adding or subtracting a positive charge. That proton has a positive charge with it, and so that's why when this bicarbonate lost an H+, it didn't become CO3 minus, it became CO3 2 minus. It lost H and plus. Okay, so since this chapter is all about equilibria, we are not just interested in the forward acid-base reaction, we're also considering the reverse reaction. So in this reaction here, we have nitrous acid reacting with water, and the nitrous acid is true to its name, and it is behaving like an acid in this particular reaction, and the water is therefore reacting as a base. Now, because we're also interested in the reverse reaction, we need to label acid and base for the reverse reaction as well. The interesting thing is that the reverse reaction, everything is flipped from what it was in the forward reaction. And this should make sense. Logically, this should make sense to you, because the acid in the forward direction is donating a proton. By definition, the reverse reaction just undoes what the forward reaction did. Everything is just going in reverse, hence the name reverse reaction. So the reverse reaction here, the thing that the acid turns into is actually the base for the reverse reaction. And just to keep them straight, we don't call them acid and base on one side and acid and base on the other side. The reverse reaction gets a special name. We call these conjugate base and conjugate acid. So the acid from the forward reaction turns into the conjugate base, and the base from the forward reaction turns into the conjugate acid. They always, always, always flip like this. And again, logically this should make sense because the reverse reaction is literally undoing what the forward reaction did. So if something donated a proton in the forward direction, it must then take that proton back in the reverse direction. So this is always going to be the case. Now, notice here, in this other reaction, now we have ammonia reacting with the water, and since the ammonia is more basic than water, now the water is acting as an acid. So back here we had water acting as a base because it was reacting with something that was more acidic than it is, but now we have water reacting with something that's more basic than it. And so now the water is acting as an acid. So again, water is amphoteric or amphiprotic. And so it can go either direction. And so in this particular case, the water is an acid, and then it turns into the conjugate base for the reverse reaction. And again, this is always going to be the case. The original base becomes an acid in the reverse reaction, and the original acid becomes the base in the reverse reaction. So, let's write out a few conjugate bases and conjugate acids. So, the fact that we're looking for conjugate base here means that this molecule is going to react as an acid. So if we're writing out a base, the conjugate base, that means that in the forward direction, this thing reacted as an acid. And so acids donate H+, so this is going to be ClO4-. Down here, we're writing out conjugate acids, which means these things are going to act as a base. So if this reacts as a base, it is going to be HCN. It's going to accept H+. So we're going to add an H, and then the negative, the Cn minus, the minus there goes away because we added a plus. And so it's just neutral now. So I would like you to pause the video now and see if you can work out the other 6 of those. So the other 3 conjugate bases and the other 3 conjugate acids. So go ahead and stop the video now and work those out. Alright. So the process for all of these is exactly the same. All of these, we're just going to take H+ away. All of these, we're going to add H+. Because that's all that's happening here. That is the sum grand total of an acid-base reaction. It's just H+ going from one place to another. So this is going to be HS minus. This one's going to be pH3. That plus goes away. And this is going to be CO3 2 minus, which we actually saw on the previous slide there. This one is going to be HSO4. And actually there's a typo there. That should have been 2 minus. Sorry about that. So that should have been SO4 2 minus. So this the one would then be HSO4 minus. This one, H3O plus. And this one, H2CO3. Alright, I hope you had the correct answers on those. Let's see, how much further do I want to go here? Yeah, we'll talk about that just real quickly. Actually, no, I take it back. I won't. Sorry to pull the rug out from under you there. I know you're getting so excited to talk about these, but you'll have to wait until the next video. So come back next time and learn about strong versus weak versus negligible acids. That will be our topic for the next video.